Sorry. Yeah, so actually this is actually indeed true. One of the still unsolved problems is like how to connect the projector to a computer. Computers get more powerful every day, but somehow that's not solved. Yeah, so first of all, I should say that, so I come from NERF, and he already introduced it, Neuroelectronics Research Flanders. We're actually founded and funded by three organizations, Carl Leuven, VIB, and IMEC. We're located on the campus of IMEC, and we also receive structural funding from the Flemish government. And, all right. So of course, when it comes to this topic, Prometheus can never be missed. There's no way around him. And of course, you all know that he is the guy that essentially created man and stole fire from the gods to give it to humanity, which in the end was essentially the beginning of human civilization. And so he is our hero, but the gods didn't really like that so much, so they punished him for stealing fire and for this transgression. And so they bound him to a rock, where every day there would be an eagle, which was the symbol of Zeus, would come to feed on his liver, which at the time was actually thought to be the site of emotions and your anima. And in this Rubens' masterpiece, actually, you can really appreciate the atrocity of this punishment very well. But I think it's also really remarkable how the humanness of Prometheus is really shown here. And today still Prometheus myth is really what stands for human quest for scientific knowledge and for progress, but also for overreaching and sometimes unwanted consequences of the quest for new things. And so this is, of course, something that I think cannot miss in this today's topic. And you've seen that theme. It seems to be very popular among people talking about the transhumanism. And actually, I mean, it makes a lot of sense because we all have accepted the fact that humans are the result of evolution. And if we think forward, of course, the concept of evolution just continuing is a very natural one. So what I'll try to do today is essentially highlight some of the recent technical advances and how they can be used to actually restore or maybe even enhance human nervous system function. And specifically, I really focus on the central nervous system, so I'm not claiming that I will cover all of the possible ways humans can be enhanced, but this is really kind of focus on the central nervous system. And one thing that I really want to highlight here actually at this point is that biology is not just physics. So there's a really, really important thing to be aware of, the fact that biological systems self-replicate and hence they evolve, and that's why we end up being here and not being stuck here. And that's one very important categorical difference to most, let's say, inanimate systems. But also, and that's maybe even more important and more deep, is the fact that actually the reductionist approach, so taking a complex problem and chopping it in smaller sub-problems, actually is not very successful in biology because we have actually not learned very much about the systems level organization of biological systems from like looking at like tiny details. And the brain is actually a wonderful example of this. Besides the fact it's just the most ridiculously complex organ that we have. There's 86 billion cells in just neurons, so those are involved in information processing in our brain, and they are connected in an insanely, I cannot even pronounce that word, insanely high number of interconnections. The important thing is that these connections are not at all random, but they are actually connected in very meaningful ways, of which we basically don't understand for the most part. And then for those people interested in electrical engineering or in computer chips, of course, it's absolutely remarkable that the whole thing runs on just 20 watts, which means like having a slice of bread in the morning and a glass of water, that will basically do the trick. And if you think about the amazing capabilities that computer is able to do, I think this is really very remarkable. And that's also one of the deeper reasons why the companies like Google or Amazon or these people are actually very interested also in understanding the algorithms behind this, because the hope is that we will be able to actually learn how to compute far more efficiently than actually our current machines do. This is, if you take a magnification, of course, this is just an example of a little bit of how this looks like inside. There's these individual cells, they have these processes, they're connecting to other cells. And then these individual cells communicate with each other using electrical signals. So in some sense, you could think of the brain as being a biological integrated circuit. And importantly, you can see that this is just a raw signal, and every time there's a red flash, that means there's like a spike, which means like a very strong depolarization. But there's also analog signals in there. So it's a mixed analog digital device that is pretty amazing if you think about the fact that there's, again, 86 billion of those in your head operating right now, to some extent at least, some of them. And not even that is enough, it's even more complex because there's not only the structure, so how these neurons are connected and their dynamic activity, but actually the activity changes the structure. So the whole thing is plastic, which means that this is actually one of the reasons why people that turn blind all of a sudden will actually be able to use parts of their brain that are dedicated to vision to improve their auditories, to improve their audition. So you can essentially repurpose parts of your brain because it's plastic. So it's not a computer, everything is set in stone, it's built once, but actually it's changed the way we use it. And so that's really a very important feature, somewhat like a self-learning machine. And just to give you an idea, again, of the complexity, so what you see here, this diagram is essentially the first steps of your visual system. So when you see something, your eye is basically here, and then the signals go in here, and by the time you go through here and do some computation, most of which we don't understand, by the time you get here, you might have been able to identify an object. And that does not mean you know exactly where you are in the room. You're not doing all these things that we easily do at the same time. Now I'm talking to you, I'm looking at you, I think I know where I am in my talk. So all of these things go on in parallel, and this is really very remarkable. And again, I think we don't really understand much of it. So then you could argue, well, he keeps on telling us that we don't understand it, so why is he talking? Of course, I wouldn't be here if I wasn't very enthusiastic about the progress that's currently being made in science, and that's really driven by three very, very fundamental, I would say even revolutions that we observe. On one hand, we have the progress in hardware, nano and microfabrication. We can make insanely small things, build small chips, make small 3D printing devices, and of course IMEC is of course one of the leaders in that arena. There's an enormous amount of progress on the neurobiology, and I will show you at least one of the tools that now is available to actually control the nervous system. We make a lot of progress in understanding the molecular parts of the brain. We have ways to change the genome using CRISPR-Cas, so we have really made quite a bit of progress on the neurobiology. And that's really driving progress there. And then last, of course, there's the algorithm side. There's an enormous amount of progress also on machine learning, or what often is grouped together into artificial intelligence. So with the data that we generate today, we can actually do a lot more than we could 20 years ago, maybe. And so we can really make progress in understanding things much better. What you see here also is, of course, a reminder of the urgent necessity of making progress in understanding the brain, because it's not always like this, but sometimes like this. So brain disease is a real issue. The cost of brain disease in Europe alone is actually more than the cost of cancer, diabetes, and cardiovascular disease together. It's about, I think, 80 billion per year. And so there's a real need for making progress on understanding the brain and fixing the brain. But of course here we want to go far beyond that into enhancing the brain. And this is where essentially you can imagine interfacing this system at multiple levels. So this is essentially a view of, if this, this box here is the human, this is inside the box, we don't see it. What we do see is actually the human interaction with the environment. So when we do things, we can see that it's interacting with the behavior. And what we don't see under the hood is all of these things. So starting with the genes that influence, and the regulatory RNA and the proteins, of course, that influence where the connections are, the synapses, that influence how these neurons are operating, all the way to the circuits and how they operate to then eventually give rise to our cognitive function. And so this is really a hierarchical system, and you can interface at many different levels. What most of the technologies do today is actually interface at the circuit electrical level. But just to give you a view, there's really, you can use many, many different physical let's say, modalities to interface with the nervous system. Electrical stimulation is obvious because the neurons communicate with electrical activity, so you can interfere with that. You can use magnetic ways to do that. There's a new technique called optogenetics. I will explain that in a second. It's also been shown that ultrasound, when it's chosen in the right power and the right frequency, can actually stimulate your brain. So there's approaches for actually modifying your brain activity from outside in a non-invasive way using ultrasound. And then, of course, chemical stimulation. You can think of pills, but you can also think of a glass of wine. It's also some way of stimulating your brain. It works extremely efficiently, I have to say. And then last, I put that here. It's not very much a technology, but I want to stress that, of course, also our human interactions, they do influence, of course, how we feel, how we think. So this is a very, very important component that we should not forget, even though there's a lot of excitement about technology. But they're very powerful. Human interactions are actually very powerful if you think of phenomena like populism or things like this. All right, so this is an exciting times, and just to convince you that indeed I'm not the only one that's excited about these times, there's an enormous amount of activities going on worldwide centered at trying to understand the brain and building new technologies to learn how the brain works, but also to actually modulate it, fix it, restore it, and enhance it. On the, say, public sector, there's initiatives in Europe and the US and all the large industrial countries. There's also on the left bottom side, there's a large number of very large and wealthy foundations that have taken that topic on. And then now, I would say that's the third thing that happened rather, let's say, since a few years, essentially the private sector starts to kick in. So there's more and more companies that are starting that actually, whose goal is to really interface with the human nervous system for a therapeutic purpose or even for an enhancement purpose. And just to give you an idea, so the Neuralink is a company that's of course run by Elon Musk, and so he has to have a company in all the cool new areas. But so this is really serious. Galvani is a joint venture of GSK, a large pharmaceutical industry company, and Google's life science arm, and they have like 700 million pounds at their disposal to invest in devices. So it's really, this is very serious. So where are we? So what I want to try now is essentially try to highlight where the technology is today, and then try to make a little bit a look forward. So what we have today, of course, and most people know this, is the deep brain stimulation device. This is a way to treat Parkinson's patients where essentially an electrode is implanted into the brain, and that electrode stimulates the brain electrically all the time. And there's a little red box that's positioned somewhere here that essentially controls what the electrical stimulation pattern will be. And in this simple video, you see a gentleman that suffers from early onset Parkinson's disease, and he has an electrode implanted, but it's turned off. And the moment he will turn it on, you will see that actually magic will happen. And he will be able to actually hold his hand still, and all this tremor, one of the hallmarks of Parkinson's, will actually go away. And this is really, I think, a very amazing illustration of how powerful these direct interfaces with the brain can actually be. And the most amazing thing is we don't even really understand how that thing works in terms of the mechanistics of the brain, but we know that it does work, and that is really, really important because that's really giving us a lot of energy to move forward. The other example that's really in use today is the cochlear implant, where essentially you have an in people that are deaf, you have essentially an electrode that directly interfaces with the auditory nerve. And so essentially you have, you hijack the system essentially in a sense that you don't need the normal sensory part of your ear that would sense the sound, but you actually stimulate electrically already the next stage, and that way you can actually overcome the problem in those deaf people. And this is chronically implanted. And this is also safe, so people really walk around with this and they use it. And I should also say, actually, the deep brain stimulation, there's more than 120,000 people that actually have these relatively large electrodes implanted into their heads. So there is clearly a way forward. So it's a reality already today that people actually have implants. Now, moving forward, of course, now it becomes really interesting because we're looking to what's gonna come, what's next. But I want to make sure. I mean, a little disclaimer. This is what I think. So please don't, I mean, things might end up being very different, but this is my best guess that I can have today of what I think is going to happen, what's going to come next. And the first technique that I want to highlight is optogenetics, which has received an enormous amount of attention. It's a bit like the CRISPR-Cas that has really propagated enormously into all labs in the world. We use it as well in our lab. And the idea is essentially that, you know, in the brain there's not all these 86 billion units, they're not all the same. But actually they come in different flavors, there's different classes, and you can see that, you know, some look like this, some look like this, and depending on what they look like, they also have different molecular properties and different functional properties, so it's quite a large zoo of these cells. Now, with electrical stimulation, you cannot discriminate because they're all electrically active, so you stick an electrode, they will just activate them. But now with this new technique, you can actually target specific cell types using genetics. And how does that work? So essentially, there's a protein that actually is a protein that makes a neuron fire when you shine light on it. So essentially, it's a protein that comes from some algae, and if you take that protein using genetic engineering, put it into the brain, you can actually make these neurons respond. And so if you assume the simple scenario of having the red and the green cells, now you don't want to stimulate all of them, but only the green ones, well, you put the channelrhodopsin, this protein, by genetic engineering only in the green ones, and then if you shine blue light, that will turn them on in a magic remote-controlled fashion. And this is now only a cartoon, but actually that really works. And this is now an example in a mouse where the channelrhodopsin is selectively put into parts of the motor system. And you can see that the moment the person starts turning on the blue light, you can see that then the animal actually runs in circles. And that is because it's actually turning it on only on one side of the brain. So you're creating an imbalance and the animal just starts running in circles. And it will actually not stop until you stop the light. So this is really a way of controlling the brain with light, kind of remote controlling the brain. But you can do also other things, even more crazy. So in this mouse, it's not in a motor area, but it's actually in a part of the brain that's related to our aggressive behavior. And if you can see that once you turn on the light, the animal will actually attack this glove. It's a glove in its cage. And normally it will just explore it like, oh, what's this? And the moment you turn on the light, it will actually attack the glove. So you can really turn on aggression with this thing. From a human perspective, you might wonder if it's also possible to turn it off. Okay, these of course are animal experiments. But this approach is so powerful that actually it's really being translated now. And so there's currently clinical trials ongoing that use optogenetics in the eye of people that have lost eyesight. And the idea is very simple. You put optogenetics by using genetic engineering tricks, you put that in the eye, and then you have these super glasses there that actually take an image of the surrounding, translate that into a pattern of blue light, and that way make you see. And there's two companies, one in the US, one in Paris, and both of them are actually having this in clinical trial now. So this is actually happening also. The next example is another, I think, very exciting example of insane miniaturization. So here, the concept of the neural dust. Neural dust is essentially tiny, tiny, tiny little particles that can stimulate your brain. And the important thing is they don't need a wire to the outside world to stimulate your brain, like is the case for the deep brain stimulation electrode, but they're tiny, just put them there, and they're essentially powered from the outside in a completely non-invasive way by actually ultrasound. So essentially you put this thing, unfortunately this thing doesn't work anymore. So you have the little dust here, and then there's an ultrasound device on top that provides not only the power to the little dust, but actually also so that it can stimulate, but it actually even allows you to read out activity. And this is an example of how the dust looks like. You can see it's really small. In principle, you can actually make it even smaller. And on the bottom picture, you see actually this is being implanted in a rat in the peripheral nervous system, where they actually use it to measure and stimulate the peripheral nerve. And this is coming out of UC Berkeley. They also just started a company called Yota Biosciences on it, and there's a lot of interest in this company. The starting point obviously is on the peripheral nervous systems. I think it will still take some time until it's put into the brain, and we can discuss the technical details if you want, but I think it's just an example of what's possible. And then in this particular, I think, example, this is about neuroprosthesis. I think it's a very impressive demonstration, again, of what you can do when you interface with the neural, with the brain. So this person has an electrode implanted into the head, and then this kind of cube coming out that actually connects to the electrode in the head. The person is entirely, cannot move at all, is paraplegic, cannot move. But now, reading out the electrical activity of the brain, this person is actually able to steer this dot. It's like this cursor, and that way she can actually communicate. So for her, it's extremely important because she can actually now much more efficiently communicate with the rest of her family. Simply by thinking of where to move the cursor, you can actually move the thing. And of course, right now you can see actually in this movie that the equipment is still kind of bulky. So this is still a big clunky thing on the head. And, but this is as a proof of principle, this works. And that's really impressive. And that's with only like, I think, 100 channels or so. So this is where I think things are heading. We can go even a bit further. This is where things get a bit odd. This gentleman, you might have seen him. And I think it's an interesting case because he makes the case that he is not wearing technology, that he is technology. This really showing the real synthesis of technology and biology, where really like the technology becomes part of your body and it becomes hard to discriminate what belongs to what. And so the story of this guy is essentially that he is colorblind, and he was sufficiently frustrated about being colorblind that he actually built this device where essentially there's a camera implanted, so it's implanted on his skull, actually. And then through bone transmission, essentially the signals from the camera are converted into vibration that essentially make him hear the colors. And so he's essentially converting the color into a sound. And you can imagine, of course, depending on what camera you put there, you could put there an infrared camera, or you could, he's essentially expanding and enhancing the ways with which he can actually perceive the environment. And I think this particular technical implementation might not be very practical, but I think it shows that, it highlights what you can actually do if you really want to. And of course, from a technology point of view, there's really a lot of challenges left, and it's actually really just a start. I mean, what we really want, of course, is seamless integration of devices, so biocompatibility, but also biostability become a real issue. We want high bandwidth. I showed you the example of the lady controlling a cursor that was like done with like 100 channels, but imagine you had 10,000 channels. You could maybe even drive your car with just thinking about it. And we don't need that, because the car is driving by itself. So you could do other useful things. So this is actually where it becomes somewhat interesting. Okay, but the battle of technologies. But okay, and the last one I think is very important as well, is that once we have devices that really interface seamlessly with the human brain, we will actually operate at high bandwidth. We will actually have to do something with the data. So we'll have to do, if you want to steer your car, if you want to do something just by thinking at it, you need to analyze the data on the fly very rapidly. So we need some real smart compute, which of course requires, again, I'm coming always back to that, of course requires places like IMEC where you can really build this next generation chip that works on the patient or on the human to really allow for direct interaction with the brain. Just one, I cannot, I have to do that. Of course, we're also active in that, so this is just one example of the device that we are building. So a little bit of advertising has to be. So this is a very nice thin film device that's only 20 micron thick, and essentially it's a plastic kind of foil thing, very thin, that in the end here has electrodes. And that would essentially go on top of the surface of the brain. That's the current thing that we built. But of course, the idea is to make a much larger one. And the next generation will be much larger. We also just won the Human Neurotech Challenge of the Wyss Foundation in Switzerland, which we are very happy about. And so I think there's really, it's an exciting times in that field. But then, of course, do we really want all of that? I think it's a very fair question to ask. Do we really want this? I think no one has a problem curing disease. But when it comes to enhancement, do we really want this? Is it really helping us? Or is it maybe not so super good? And if you just think back of the 50s, at the time people thought, okay, well, we're going to have atomic cars because the people thought atomic power is just super. It will solve all problems. Turns out, maybe not. And cars are actually still an unsolved problem. But there are clearly a lot of implications that come with these technologies. And just to mention one, it's actually a kind of a very obvious one is the question of safety, right? So there are actually communities on neurohacking. So there's people that actually meet together and they solder up some stuff, and then you don't need much technology for that. You need a battery, and you can change the way you think, basically. And so there's like they meet, and then they exchange recipes. It's a bit like exchanging recipes for cooking, and then it's about mindful. You can enhance your ways, and people exchange how they can do it and what's the right stimulation current for which person, which is very interesting. But of course, it's also really, really, really crazy because you might as well also do something that you cannot control very well, and you create a seizure or something like this. So medical safety, I think, is a very obvious one. But it's far broader than that, actually. And these, I think, are the much more serious ones. I think medical safety is an issue that we've, as a society, we have already found a quite decent solution for it, which is regulating medical devices. So there's a European medical device regulation, and if you want to sell something, you have to have an approval, and that means someone will check that thing, and it will be really checked whether it's going to kill you or not. Now, these are, I think, much more far-reaching issues, and I group them essentially into three areas. One is, I think, the privacy and consent. So who owns your neural data? If I can read out your brain at high resolution, and I can actually predict from that the things you will like, the things you will do, who owns that? Of course, you would argue, well, you own it, but if you think about Facebook, actually all your data is owned by someone else. So I think there's some action needed to make sure that we own our neural data. Can you predict personalities? Will this be important for insurances? Will they say, no, that guy, we shouldn't insure this guy's car. He always drives a bit too crazy, or he's not paying enough attention. He's not able to pay enough attention. So these, I think, are very real, potentially real problems. Of course, then also, if you have a device that reads out your brain, can you track? Can I track when he drives home and say, oh, he's now thinking of that. Oh, he's writing his book. I would write it differently. And then I hack into his brain, and then I make him write the book in a bit more positive way. So these are, I think, I'm kind of joking, but I think it's very real. And I'm just trying to give you a sense of, that these are actually real questions. Then, of course, on the other hand, we have the agency identity questions. If you have a device implanted and that changes you, and we know already actually from the deep brain stimulation patients, it does change personalities. So the deep brain stimulation that's used today in quite a substantial number of patients actually change their personalities. They start to become gamblers. They do behaviors that they didn't used to be doing, simply because there's an electrode that stimulates and we don't really know exactly what it's doing, and there are side effects. And so if you have a device, and let's say because your device is not doing the right thing, you hit someone else, or you drive with the car somewhere else, like who's in charge? Is it you? Or is it the company that built the device? Or is it the surgeon that put the device in? I think there's a lot of questions. If you crank up maybe the current too much, I start around and killing people, and then I said no, it was just a device. Someone turned on the current too much. So I think there's some real questions about self-identity and responsibility that we are not prepared, I think, today to address properly. And then I think there's a very important societal aspect to this, which is, of course, and that's true somewhat to all technology, of course, but I think here is particularly dramatic, is, of course, technologies are typically expensive, certainly when it's pioneering technologies. And so then the question is like, who will have access to these technologies? Will there be a form of reimbursement, or will only the rich people be allowed to enhance their mental abilities, creating new classes in societies where there's the rich guys that can enhance their brains, and there's the poor suckers that cannot afford it, and they will just always be overruled. And so a new way of dividing. Of course, this is a terrifying scenario for me. And then maybe the last thing is like also the brain doping. If you think of, let's say you have an exam, and then the professor asks all these really difficult questions, but I can solve it because I have the chip in my head. And then is that fair, or is that not fair? because I am still doing it. I'm still answering myself. So is that okay or not? And I think these are really the kind of questions. That's why I put them here, that are really unique to neurotechnologies. They're not generic to just new technologies and us not knowing what to expect, but really they're very generic because they're very unique because once we start interfacing with our brain, with ourself, everything changes. Now the last slide I want to highlight, we are also organizing a really fantastic meeting in this fall. If anyone is interested in really looking into what's the latest and greatest on neurotechnologies, please come to Leuven in October. This is really organizing with like the top journal in the field and bringing all the international leaders to Leuven and to discuss mainly the technical aspects, I have to say. But yeah, so if you're interested, please come. All right, thanks.